So it is my absolute pleasure to introduce our speaker for today, my esteemed colleague, longtime collaborator, and good friend, Professor Paola Caselli. Paola is presently the director of the Center of Astrochemical Studies at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, and an honorary professor at the Ludwig Maximilian University in Munich. She obtained her PhD from the University of Bologna, Italy in 1994, after lengthy pre-doctoral appointments with Eric Herbst at Ohio State University and Phil Myers at the Smithsonian Astrophysical Observatory. Prior to becoming director at MPE, Paola was a researcher at Arcetri Observatory in Florence, Italy between 1996 and 2005, and a professor of astronomy at the University of Leeds in the UK between 2007 and 2014. A world-renowned expert on astrochemistry, and in particular how it relates to star formation, Paola will present to us today a talk entitled From Clouds to Planets, the Astrochemical Link. So without further ado, I now turn the control over to Dr. Caselli.
So I wanted to say that I'm happy to be here and try to make links, and not just from clouds to planets, but also to the NGVLA, which is some kind of the dream telescope for me, as you will see in this presentation. So. Of course, there is not much time to go into much detail in all these various figures that I'm showing here, but I will take you from, say, clouds scale to actually protoplanetary disk scales and make some links also to our solar system. And we will see that indeed we really need to have high angular resolution and high sensitivity telescopes to do things properly. So let me start actually at the cloud scale with some new work that is done by a student in my group. So Spandan Chowdhury, who is working closely with Jaime Pineda. And so we are here in, just give you an example of an important connection between cloud scale and now dense core scale. You know that dense cores are the units of star formation. But there are lots of things that they have been studying since decades, but there are lots of things that still we do not understand. And one of these is indeed their connection to the cloud. This is, of course, very important because we want to understand how, for example, they form, how they accrete their mass, and how they evolve. And without this understanding of their physical structure, including density and temperature, it's really hard to actually make also predictions, theoretical models, comparison with simulations. So Spandan, what he has done, he has used data from the GBT ammonia survey that is led by Rachel Friesen and Jaime Pineda. And here you see one example. This is a beautiful cloud in part of Ophiuchus molecular cloud complex, is L1688. And now you see here the Mach number that has been measured using ammonia 11 lines. One thing that you can notice here is that there are these dark spots that are the so-called dense cores. So these are coherent cores, and they are marked by this black line because they are cores, say their line widths are actually subsonic. So you can see, in fact, that the Mach number in this course is less than 1. So until, say, a few years ago, or a couple of years ago, we thought all that this transition from core to cloud was very sharp. And so the transition to what we call the coherence was very sharp. But in fact, with the high sensitivity observations done this time with GBT and smoothing the beam, because of course we need the signal to noise, Spandan was able to find actually that there is not just, when you look at the ammonia line, you are not just viewing the dense core, but you are viewing also the cloud outside the core. So he was able to decompose the ammonia line between the dense core part and the cloud part. And you can see, but to do that, you really need the super high signal to noise measurements. And you can see here that the cloud is actually at a level that you only can see this if you smooth across the whole core, basically, with this data. And you can see that the cloud is affecting the line profile, which means it affects also the temperature that you measure with the ammonia. And of course, also the density profile and what we know about this core. So it's very important to have this high sensitivity, and I didn't write it because it was too long, but a high spectral resolution observations. So this is a requirement that I really hope that the NGVLA will provide, because this is very important for this connection. Now, I want to go now to slightly lower sizes, and now is the dense core size, so from cloud to core. And another important aspect that we learned recently is that in this transition phase between dense cores and the molecular cloud just around, we actually see complex organic molecules. So this is the COM that you see here in the slide. So the complex organic molecules, the definition of them is that they have, of course, carbon atoms and in there, and there are at least 6 atoms in total as the size of the molecule. So one thing that we found out with using ALMA is that, for example, if you use dense cloud tracers like, for example, deuterated ammonia, but also the ammonia is very good to trace the core, you see the high density region. So this is actually the upper panel here, where you see a very well-defined center of this core, which is HMM1, still in Ophiuchus. But when you look at the bottom panel, you see actually the methanol line, which is one of the simplest complex organic molecules that stays on one side and really traces this transition between core and cloud. Now, you see still here in contours the ammonia distribution. Now, what we have learned since now several years of observations, and now ALMA also is, say, able to at least measure the simplest COMPs in these regions, is that these COMPs indeed form in starless cores. So in these cold environments where the temperature is about 10 Kelvin and the densities are a few times 10 to the 4 per cubic centimeter, this is the ideal place where to find these COMPs. And you can see that many authors have used single dish telescopes to do that. And of course, one thing I can say is that NGVLA will be super good to do these type of observations. And in particular, it will not just be able to observe COMs, but we will enter the regime of the prebiotic molecules that unfortunately until now it has been really hard to see. And these cold cores are particularly good for this because their spectra are, how to say, you don't have super crowded spectra in these regions because the temperature is low. So you actually get the chance to detect very complex organics at low frequencies where they in fact have their say, highest emissions in these regions. So this is another thing that we need to improve. We understood, I think, so far why this is happening, because of course the question is how do you make these complex organics in these regions? And we understood this with some simple chemistry applied to say cores like starless core or prestellar core with the density and temperature gradient. And what we understood is that these complex molecules tend to form in the region where the CO start to catastrophically freeze out. So at the edge of these dense cores, where the temperature, as I said, are very low, and the volume density start to be a few times 10 to the 4 or higher, you have the so-called catastrophic CO freeze out, and the ice mantles become CO rich. In these regions, you have the hydrogenation of CO that happens on the surface, so you form methanol. Part of the methanol can desorb back in the gas phase, and that triggers the formation in the gas phase of other complex organic molecules. So this is an example here that I hope this is a little bit, it's not a great movie, but it's just to show the evolution as a function of time of the abundances of various species as a function of radius in a prestellar core, showing that with time, and we stop the say the simulation when the CO column density that we have measured is actually the same as the one that the model provides. You see a peak just outside, so here is about 0.1 parsecs away, so at the edge of the core, where in fact you start to see this CO complete freeze out. Behind this model, there are lots of things, and of course I have no time, but I underline that to do this type of modeling, we need measurements from the lab, we need say experimental work, but also theoretical studies about, for example, neutral-neutral reactions that are very important for our understanding of these regions. So now let me go a little bit below 0.1 parsecs here, and we are getting now into the central region of this prestellar course. So actually, I should make a distinction because, you know, people talk about starless cores and prestellar cores almost interchangeably, but actually we should be careful because we have the definition, a prestellar core is actually a subsample of a starless core, and it's, there are very few prestellar cores, those that we define as prestellar cores, so regions where the central density are higher, the same or higher than 10 to the 6 H2 molecule per cubic centimeter, and so their lifetime is very short because they are going to form a star soon, and this is why they're super interesting, because they can actually provide us with the chemical and of course the chemical inventory, but also the kinematics, and linked to the, say, dynamical evolution of the central region that will in fact form a protoplanetary disk soon. So you can see here that since many years we have been studying this type of cores, and we know that the central region are very well traced by deuterated molecule, and this is again due to some interesting chemistry, simple chemistry fortunately, due in fact to the high density, low temperature, and a large amount of CO freeze out. And this is another thing where, say, NGVLA will actually give a great contribution, because as Rachel Friesen wrote in 2018, as part of the NGVLA book, there is a very nice table where you can find lots of interesting deuterated species, especially the ground state transitions, and many of them can actually be observed between 60 and 110 gigahertz. And so these could allow, for example, NGVLA to do detailed mapping using a large variety of deuterated species from more than 10,000 AU down to 100 AU scale, which is fantastic. So we know that prestellar cores have a sharp, well, say relatively sharp temperature gradients. We found that, actually Antonio Crapsi found that in 2007 using VLA. And we have been, in fact, trying to, enlarge the sample here, and but of course, with the higher resolution and the higher sensitivity, you can actually really enhance the sample of objects where we have the temperature data. So you can see here that if you look at, say, single dish observations, you can actually arrive at wrong conclusions in terms of the temperature structure, because you are not sensitive to the central region that are centrally concentrated. That's why the single dish doesn't see it. And you, in fact, with the VLA, we got this beautiful data, the red data that actually are consistent with predictions from radiative transfer model. And you can see, this is the green curve here, and you can see that the temperature goes down to 6 Kelvin in the center. This, of course, implies large CO freeze out. And so dust grains that have thick icy mantles. And also, this induces a large deuterium fraction, as I already mentioned, with D over H larger than 20%. And this 20% you should compare with the D over H cosmic abundance that is abundance ratio, which is about 10 to the minus 5. So it's super important. Now, talking about going deeper and deeper, and this is again something that it will be fantastic to do also with the NGVLA. I mean, these are ALMA data that we took some years ago and show now in detail the central region of this prestellar core. This is the L1544 in Taurus with 8 solar masses. If you just use a single dish and measure the mass inside, say the C18O line, 1 to 0 line, you have 8 solar masses. However, if you use ALMA, you actually get only the very center. And the center, we call it the kernel. And this kernel is only a small fraction of the total mass, it's 0.1 solar masses. But this is fine because this is actually the thing that we want to study to actually get to the protoplanetary disk, the initial conditions of this protoplanetary disk. Now, using a non-ideal MHD simulation, we were able actually to reproduce the flux that we see with ALMA. Here, this is the ACA main array and the ACA plus main array combined. And we found that actually you have to have a region where you, with central densities, peak central density of 10 to the 7 to reproduce the flux that we see. And this region is flattened. We kind of see it with ALMA, but I think we need to get even, say, more sensitive observations here at 1 and also 3 millimeter emission. Now, more recently, we detected the deuterated ammonia with ALMA using a mosaic. So we have a very good, actually, we are recovering all the flux, as you can see here, for the spectrum that I show here. And one interesting thing that we found is that the deuterated ammonia that was supposed to be peaking at the center of this core, there is actually a valley in here, and it is consistent, in fact, with freeze out, which is now, say, the first time that we can see now with these sensitive observations, this central region where the deuterated ammonia is missing. And using comprehensive modeling, including, say, of course, the surface chemistry, gas phase chemistry, gas-grain interaction, the physical structure of the core, and also the radiative transfer, we were able to reproduce the data that we observe in this prestellar core. You can see here the black is the observation and the red is the simulated the spectrum at these different locations here. And these data are reproduced with the profile of the deuterated ammonia that is actually decreasing from, say, about 7,000 astronomical units down to the central region. But at about 2000 AU, we have this catastrophic freeze out again. So then the question was, what happened to the other species? And are we actually able to have some tracer in this region? And the answer is that if our models are correct, then most of the species, actually 99.99% of all species heavier than helium, are frozen in the central 1000 AU of a prestellar core, which make things, of course, interesting, because this could tell us that, in fact, in the center of these regions, you have very thick, I already said that you have thick icy mantle, but now I'm talking about very thick, 150 or more monolayers of ice on top of our dust grains. And of course, this could promote dust coagulation and possibly the formation of structure that allow the preservation of this ice into later stages of, say, planet formation. In fact, with the NGVLA, should allow, with the high sensitivity, I hope, to study indeed grain growth at a much higher level that we can do now. And of course, we have JWST that will measure ice toward this highly extincted region. So we will have all we need to test our models and understanding of how these icy layers are composed, what are the molecules inside there, and which will be the, what it will be the form of dust that will going to form then the protoplanetary disk. So this is the last part of my talk, just a few minutes to get into the next stage. Of course, again, things are very complicated. We need models that take into account, simulations that take into account the non-ideal magnetohydrodynamics, because we have magnetized clouds, slightly ionized. So this, of course, makes the formation of protoplanetary disk, if you don't have non-ideal effects, very difficult. And we think that, in fact, already in, in 2009 to 2011, as written here, when we studied the self-gravitating disk, when I was back in Leeds at that time, that actually at the beginning, so when you actually form a disk, because of the large amount of material that is in falling and accreting onto the disk, this disk most likely will be probably self-gravitating. Of course, there is not much, evidence of that, but we are keeping accumulating this. And so with Bo Zhao, when he was at MPE, now he's in Canada, working with Ralph Pudritz, and he did beautiful work on taking into account this magnetization and non-ideal MHD to understand the formation of protoplanetary disk. And the interesting thing was that actually to be able to form these disks without dragging inside toward the center too much magnetic field, we needed to get rid of the very small grains, so these 10 to 100 angstroms. So here, just to give you an example of what happens if you keep the very small grains into your simulations, so you have beautiful outflows, but you don't have disks at all. They are very short-lived. But without the very small grains, you can actually prevent these magnetic field lines to concentrate toward the center, and you start to form self-gravitating disks, in fact, with spiral arms, and you can have all shapes you want, changing a little bit the initial conditions that, of course, we don't expect to be all the same for all these objects. So, and this is very recently, this is Joaquin Zamponi, again in my group. He's working with Maria Jose Maureira, and he has been working on very high angular resolution observation of a famous class 0 source, IRA 16293b, ALMA observations. And here, what it was found is that the brightness temperature at 3 millimeter is larger than the brightness temperature 1 millimeter. And of course, a 3 millimeter probes deeper layers of the disk. So this is indicative of hot mid plane. And we were able to reproduce this type of observations and brightness temperature using radiation hydrodynamics of self-gravitating disks. And of course, if this is the case, you see the temperature here, we are talking about several hundred Kelvin in these initial phases. So we expect that a large part of this icy mantle that were formed at the beginning, have been evaporated, and also some carbonaceous grain destruction. Now, to prove this, again, this is a problem because these disks are very optically thick. So again, another topic for NGVLA, that this will be, in fact, fantastic to probe deep with, super high sensitivity, and also look into the evolution of the dust. So now you can tell me, well, I mean, you just told me that you are making all these nice icy grains, and then you make the protoplanetary disk, and everything is going off back in the gas phase. So who cares about these initial conditions? But actually, we do care, because as Jaime Pineda has recently found, actually this this keep accreting material, and not just from the cold envelope, but also from the molecular cloud. So this is an object well known from SMA observations. Here, this is the beautiful outflow. And what Jaime found using the NOEMA interferometer, IRAM, here in Europe, you could see a nice line of HC3N, the 10⁹, that actually is really consistent with the accretion of material from more than 10,000 astronomical units, so the edge of the core. So you are keeping replenishing with icy grains anyway this central region. By the way, this little thing in the middle is one contour of the 1.3 millimeter dust continuum emission from ALMA. So there is the need of linking this scale. And I cannot finish without mentioning then the next step, which are the protoplanetary disk. This is the beautiful work done by Dominic Segura-Cox, who has used ALMA to actually discover that the youngest protoplanetary disk so far discovered with the substructure. So we don't only have, of course, the well-known HL tau with these beautiful rings, but also in the class 1 stage, you can have a substructure and maybe also deformation of protoplanetary disk. So here, what NGVLA will do is that we'll connect now the outer disk that is well studied by ALMA with the terrestrial zone, as Di Francesco wrote in his paper talking about, in fact, the VLA capability. And this will be fantastic because there is, of course, accretion of material coming from the outer part of the disk toward the center. And this is what we wanted to understand to actually put the dots together, link the dots, and understand how terrestrial planets like our Earth is formed. My final slide, sorry, of course, I'm a little late, is about this correlation. So this is one of the first things that we see now. So correlation between the comet. This is the famous 67P comet that was visited by Rosetta, and this is the ALMA protostellar interferometric line survey done by Jes Jorgensen. And you can see that the complex organics, when you plot them together, they are on this close, relation that shows that indeed, as they say in this paper by Drozdovskaya et al., the composition of cometesimal and planetesimal is partly inherited from the prestellar and protostellar phases of evolution. But this is an hypothesis. We don't know the details and indeed if, what happened during all these steps. So I arrive at the conclusions with the connection again with the GVLA and GVLA. So here is what can we do for starless cores? Well, lots can be done still. And for example, deuterated molecules, tracing the whole scale from more than 10,000 to 100 AU. We can understand the origins of these prebiotic molecules, dust evolution, core cloud connection, and of course, the initial condition of protoplanetary disks, which is still like my kind of holy grail. Protostellar cores within GVLA, well, the connection again, cloud to disk, and with the same tracer, really go similar to the starless cores, but now to even smaller scale, the scale of the disk, the effects of accretion onto protostellar disk and also on chemical evolution. For protoplanetary disk within GVLA, of course, COMS and PBMs, these prebiotic molecules, we want maps of them and understand how they change across the disk. We want to zoom in on snow lines and understand their structure, gas and interaction with the dust and dust properties, the terrestrial zone and connection with the outer disk. So this is the last slide that I showed before. So we understand now that COMS in comets are similar to those in star and planet forming region. So we need to test this kind of hypothesis that inheritance from pre and protostellar phases is indeed taking place. Thank you very much.
That was excellent, Paola, as usual. Beautiful, beautiful data and results. So we have a couple of questions that have been entered into the Q&A box. Do we know if the growth of icy mantles followed by their evaporation promote the growth of the refractory grain core? Or does the refractory part shatter when the mantle evaporates? That is there a lasting impact on the grain size distribution in the protoplanetary disk?
Right, that's such a great question. I really, yes, this is something since we were doing this self-gravitating disks and see that the temperature in these disks are really high as predicted, but now we start to see them, so they are there. There is a phase that you have. That's exactly what we need to worry about. I cannot answer the question because exactly this is, I can tell, I don't know. I have been thinking a lot about that, and I can tell that one thing that could happen, especially in the very early phases, even if you so the central region of prestellar core where you get this growth of grains, so these grains that will actually enter first in the disk will actually lose their memory because they will lose their ice, and also they will fragment again. So even if there was some growth because of the ice was actually acting as a glue, losing the ice, they will probably go back to the initial kind of MRN distribution or something like that. But whoever asked the question is right, because if the temperature is high, so you may start to lose the carbonaceous grains, as we have seen also from other papers. There was a recent paper by also Van Hoff et al. That also found, say, warm disks. So above 300 Kelvin, you have this soot line, and then you enrich the gas phase in carbonaceous material, you may actually start to form a different type of dust, because of course you have the high densities and you may have conditions that are actually not so different from what you have in say a part of the outer layer of these AGV stars, where you actually have the formation of dust. So you may start to mix up ingredients, and maybe the high temperature of the dust indeed may promote stickiness, but that is something that we don't know yet. Great, at least I don't know. I mean, it'd be great that somebody in the lab could try to do this type of experiments at a higher temperature, say above room temperature, or say 400, even 500 Kelvin. So I hope we will answer soon this question. Of course, observations will help, at various wavelengths and low wavelengths as well, because we really need to go to low wavelengths to reach the mid-plane of these young disks that are completely obscured because of the optical depth.
Okay, thank you, Paola. So the next question, very interesting to see the interplay between regularity and structured behaviors. With NGVLA, will it be important to monitor the chemistry in any of these systems? That is, will the chemistry vary on astronomer lifetimes in appreciable and important ways?
Well, I mean, there are, I think the answer is yes, somebody should do it, especially for in the early phases of this protoplanetary disk formation, where you have lots of going on. I mean, I think the time scale there for every process is really short. So it could be great, I think, to have a monitoring, because also, as many people in the audience know, there is, of course, episodic accretion going on. These disks, in fact, even in the simulation, we see them, even in our, in Bourgeois simulations, we're seeing that if you have a self-gravitating disk, quite often, so quite regularly, you form these clumps. So these are the fragments due to the, say, self-gravitation of these disks that form, and then they migrate toward the inner part, and then they accrete onto the star. When there is this accretion event, you have a lot of say energetic phenomena going on. Of course, you have a stronger jet, a stronger irradiation, X-rays, energetic particles, and this will affect the, say, chemistry in a short time scale. So it will be great to monitor. I know that there are efforts that are already in place. For example, Ilsa Cleaves Virginia, she's actually doing that. I don't think there are many people doing that with her beautiful HCO plus monitoring. And I think that is the way to go to, if we really wanted, for example, to connect how the episodic accretion affects the chemistry, and not just the chemistry, but also the dust properties and everything that then will go later on into the formation of planetesimals and then planets, especially in this terrestrial zone, the zone where terrestrial planets will form. So yes, go for it.
Yeah, I think that would be fantastic to see chemistry evolving on almost day-to-day timescales, especially with flare-ups of stars, evaporating grains, and then caught those mantles, and then the gas would then slowly freeze out again. It would be fantastic to see. Okay, thank you for that question. The next one is deuteration of polycyclic aromatic hydrocarbons important?
So pads, this is what I like to call them, or I think people call them, instead of pHs, you have these PADs, pads. They are, so we think they're there. There have been studies also with Bruce Drain actually doing some observations together with other people and trying to find some evidence. And it seems that there is a good reason to believe that indeed they are there in the interstellar medium, because of course there is the exchange between the hydrogen and the deuterium that is always, say, energetically favorable. So you may actually end up enriching them. But the thing is that you have to be in a dense region where for example, again, in a cold zone to do the enrichment properly, because otherwise you will probably have pads divided pHs that is the same as the D/H cosmic abundance. This is what I would expect in interstellar medium, maybe slightly more because of the HD interchange. In dense regions, unfortunately, we have no clue, because it's very hard to detect these paths. Of course, I mean, I would ask Brett McGuire and the whole team in Virginia and Harvard to actually put an effort and observe for lots of hours at GBT and try to actually find some deuterated forms of these organics, beautiful organics that they have detected recently. So if you just ask me what I think it's happening, I think yes, they are going to get deuterated in the dense regions of starless cores and prestellar cores, with the simple reason that I expect that they will freeze out as CO freezes out and all the, say, heavy molecules will freeze out. And once they are on the surface, the deuteration will be very rapid, because in these regions, the atomic D/H ratio is expected to be orders of magnitude higher than the cosmic D/H. So I'm talking about the D/H atomic. So you have a lot of D atoms floating around, which of course will compete with hydrogen when they say hit the grains. And this DH exchange reaction may indeed happen on the surface, and you may end up with the deuterated pHs in the ice. Now, if there is a way to detect this, maybe that's actually a good, now I'm thinking while I'm talking, I think it would be great to start making measurements of these pHs in ice, including the deuterated ones, to make predictions for when JWST will fly. Not that, I expect to see them very clearly compared to other bonds that we will see, but that could be a possibility. So somebody in the lab could try to do that and make predictions for JWST. Yeah.
All right.
I'm sure I have not answered the question, but there is no answer to the question.
There was no elaboration about importance, but I think you did a great job, Paola.
Okay.
So,
thank you, James.
So I have a question, and I wanted to ask a little bit more about that wonderful slide you showed of I think it was HC3N streamers that were converging onto,
Yeah, this is Jaime's work.
Yeah, I just wanted to ask, and maybe you said this very quickly, but is there actually evidence that that streamer is moving towards the core through velocity gradients or something? I just didn't.
Yes. So what Jaime did, indeed, he used a model just considering, say, a parcel of material under the influence of the gravitational field of the core and the protostellar core. And he could actually model this, the velocity gradient, say, of this streamer very well with this simple, say, model. So indeed, there is evidence that also looking at the velocity, say, at the very top, so when the filament, this streamer, is actually connecting to the outer edge of the core, there is evidence that indeed the velocity is close to the, say, outer cloud, say, to this connection between core and cloud. And then the velocity changes all the way toward the central region. Now, the angular resolution of NOEMA does not allow us to actually check the landing point of the streamer onto the protoplanetary disk that is there. But of course, there are now more observations going on also with ALMA to try to link this. So the answer is yes, there is evidence that this is material. So I could consider this, maybe to make things simple, like asymmetric accretion of material onto the core that then is, say, all the way. So it's like, James, you know this, because we have seen this also in the past. I remember there was Swift observation. You remember Jonathan Swift? He did observations of, I think it was CCS. And I remember this beautiful paper where he showed this little cloudlet in CCS that has shifted the velocity compared to the dense core. And this, so you have to think of this material as little cloudlets that are at some point, passing by, or, the cloud is probably clumpy by itself, and then when they get close to a, say, gravitational potential well, they are gravitationally attracted to that and just accrete. So instead of spherically symmetric accretion, we are witnessing this asymmetric accretion. And one clue is the fact that you have HC3N, which is typically not seen in these very dense protostellar cores, because HC3N is an early time molecule. So that was the other thing that made say, the news in a sense.
Yes, I was quite struck by that. I was also wondering if there was an abundance gradient in the HC3N along the streamer. That might be hard.
That's very difficult to tell, because, in fact, I mean, the way forward here is well, it'd be nice to have, for example, continuum emission, but we don't see the continuum emission, of course, just along the streamer, okay, because you are not seeing any enhancement, local enhancement, like we don't see it, for example, in C18O with these in these sorts. One way is to look, for example, at multi-transition of the same molecules and follow it down and look at this, for example, density gradient, and try to compare with other molecules and with the same density, say, similar density tracer, to see variations. But otherwise, yeah, I think it's difficult to do.
I would think maybe comparing to ammonia itself would be interesting. But anyway,
yeah.
That's fantastic.
Yep.
But we have more questions. So I'll return the floor to others. And the next question is, the plot of increasing molecular complexity you showed last was very interesting. Have you thought about what are the most likely molecules of biological importance the NGVLA may find?
Yes, that's a big question mark. So there are, I would say, if I had to start to do this type of research, I would actually talk to my colleagues in Madrid, and in particular, this is Victor Villa and Izaskun Jimenez Serra. They have been doing this beautiful work on looking for prebiotic molecules in one of these relatively quiescent regions in the galactic center, and they have found several interesting molecules. And of course, this is not just them. I mean, it's just that many other groups are doing it, including, of course, Tony in Virginia and Brett, etc. But what they're doing, the reason why it came to my mind after this question is that I have seen in their talk that they start with the diagram, and this diagram is the formation, the formation path of nucleobases that was done actually by Pounds and Powner and Sutherland in England for the origins of life. So they were really looking into these steps and see which molecules are the intermediates to actually arrive at the nucleobases that we have in our RNA and DNA. So in this scheme, of course, I mean, I don't remember now all the names of the intermediate molecules, but I would say that this could be the right way to go and start with, precursors. And of course, also attempt to do, for example, some famous amino acids like the glycine that we even thought that we were able to see these prestellar quartz, because the prestellar quartz are in fact the regions where you expect to identify much more clearly all of these transitions. So I could go for, of course, the glycine, so amino acid, the simplest amino acid, but also for, precursor of nucleobases, and also not just the nucleobases, but also parts of the other parts like the sugars that constitute, our DNA and RNA. So there are lots of molecules, of course, one can choose from, but maybe just focusing on those that are relevant for us as a first step, I think that could make sense. Purine, pyrimidines, and of course there is already a lot of work that has been started with the GBT, but NGVLA I think will do much more on this side.
It's very exciting. Very exciting.
Very exciting, yes.
Okay, we have just one last question.
Sure.
Paola. This questioner asks, can you please tell us a little about the artwork that you have as a background?
I cannot tell much. So the only thing I can tell is that this was done for a conference that was in Munich about the origins of life. And this was led actually by my biophysicist friends in Munich. And one of these people, so one of these biophysicists has a very good friend who is a painter, and she just, she doesn't know much about science at all, but she understands talking, of course, with people in this origins of life field, to learn about molecules, and then the earth, the importance of water. And you can see that in this artwork there is basically everything, sort of, so from the simple molecules to the complex molecules to more kind of DNA type of maybe protein shape entanglements here, and water and rocks and exoplanets. So I thought the reason why I use it is because of the colors are so beautiful.
Okay, thank you, Paola. That was great.
Oh, thank you.